Swayam Prabha. Digital India. Educated India.
Hello students, welcome to this lecture. In the last lecture, we started discussing rotational spectroscopy, but before we could go further into rotational spectroscopy, we spent some time in classifying the molecules into different rotors. For example, if you just to remind you that we had linear molecules representing a class by themselves, followed by another class of symmetric tops, where the principal moments of inertia had a particular relation that we discussed. Among symmetric top, we had prolet or oblate type of molecules. We also had spherical tops, where the moment of inertia along all three principal axes were equal to each other. And finally, when those molecules do not fall into any of these three category, we call them asymmetric top. So, in today's class, we would discuss rotational spectroscopy, but before we go for larger system, we will focus on diatomic molecule. So, that is the topic of our discussion now. We will look at the rotational spectroscopy of diatomic molecules. When I have diatomic molecule, for suppose to keep it general, let me call it, I have a system like AB and I am rotating this molecule. Of course, I know there are three principal axes around which I can define this rotational motion of this molecule. One of these principal axis is along the internuclear axis, the other two are perpendicular to the internuclear axis. Now, when I rotate this molecule around IB or around IC or the principal around two of these principal axes, what I would get is that the molecule is showing end over end rotation or the rotation around its own bond. In any case, I can define this rotational motion the way we discussed the rigid rotor problem. As long as A-B bond distance is remaining constant, we can discuss the rotational motion of this diatomic molecule through the rigid rotor problem that we discussed earlier. In case of rigid rotor, we had the Hamiltonian, which had only the kinetic energy, where this is the Laplacian, which is the second derivative with respect to the three Cartesian coordinates, the kinetic energy operator. Once we solved this problem, we obtained the solution as this way, where these are the eigenfunctions and these are the eigenvalues. So, the energies were expressed in terms of j quantum number, where it is j into j plus 1 h bar square divided by 2 I, where I is the moment of inertia. Now, the values of j goes from 0, 1, 2, so on and so forth. For each value of j, we have 2j plus 1 number of mj values, where mj values goes from minus j to plus j in the step of 1. So, therefore, for each j value, we have 2j plus 1 number of levels. So, the rotational levels are 2j plus 1 fold degenerate. Now, what about this? We will come back to this wave function. Just one more point here. We express this in terms of energy, but since now we are discussing spectroscopy, these are going to be the stationary states from where the transition will occur. So, let us express these energy levels in terms of their wave numbers. So, the new j bar is obtained when I divide this E j with h c, because the energy and wave numbers are related this way. So, I have j into j plus 1 h bar square to I, now multiply that with h c. So, when I look at this, h bar square is h square by 4 pi square. So, I would be left with h divided by 8 pi r square I c. So, where c is the speed of light, I is the moment of inertia, pi is the constant, h is Planck's constant, multiplied by j into j plus 1, and this constant, when for the particular system where moment of inertia is known. So, this becomes a system specific constant. We call that constant B or rotational constant. The energy becomes B j into j plus 1, and this B, and therefore, the energy over here is expressed in the the B as well as the wave number here are expressed in the units of centimeter inverse. So, this is the energy level. Now, let us look at these wave functions. So, if you recall, these wave functions were simply the spherical harmonics. So, they had some beautiful properties which we would be using to discuss about the selection rules. So, now let us look at what is selection rule here. We discussed in our earlier class. So, when we have when we are carrying out any spectroscopy, we would be interested in evaluating this transition dipole moment integral, which is simply described as the following dipole moment integral. So, suppose I am starting from suppose I am starting from a particular stationary state, in this case a rotational state, whose quantum numbers are given as j double prime and m j double prime, and I am going to the final state whose which is again a stationary state, and in this case a rotational function, eigenfunction, whose quantum numbers are given as j prime and m j prime. So, when I do this, when I make a transition from the initial level to the final level, of course, the electric dipole moment of the molecule would assist the system to communicate with the electromagnetic radiation and therefore have this transition. So, this transition dipole moment will tell whether this transition is allowed or not. So, if this R is 0, then we would know that this is a forbidden transition, or if this transition is not allowed, and if this R has a large value, R square is proportional to the intensity of the transition. So, therefore, if R is large, the transition is a strong transition. So, now when we look at this, what about mu? We know that mu has would have 3 components, mu x, mu plus mu y plus mu z, and of course, now if you recall our discussion, we expressed this Laplacian from Cartesian coordinate to spherical polar coordinate system. So, in the r theta phi language, we would have mu x as mu multiplied by r sin theta cosine phi plus mu r sin theta sin phi, which is my y, plus mu z, which is simply r cosine theta. So, now in the operator part, I have these 3 terms to put in. So, what about the functions here, psi j prime or psi j double prime? These are simple spherical harmonic functions. Once I do this calculation of these integrals, I would see that R will become 0 unless the following condition is satisfied. Unless delta j, that means j double prime minus j prime, unless delta j is plus minus 1 or delta m j is 0 and plus minus 1. So, unless these 2 conditions are satisfied, R will become 0. So, therefore, this is a selection rule, a set of selection rule that I will follow for the transition. This is a specific selection rule, but then there exists another gross selection rule, which if you look here, this transition dipole moment integral, I do not have to expand this mu into mu x, mu y, mu z if mu itself is 0. So, if the molecule does not have a permanent dipole moment, so the mu becomes 0. So, its 3 components are also going to be 0. So, in that case, if mu is 0, then R becomes 0, and then therefore, this is not an allowed transition, and the molecule becomes rotationally inactive or microwave inactive. So, for a molecule to show rotational spectroscopy, it must have a permanent dipole moment. So, permanent dipole moment is a necessary condition. to show rotational spectroscopy. So, therefore, if I am considering diatomic molecules, homonuclear diatomic molecules like A type, let us say oxygen or nitrogen molecule, they will be microwave inactive or rotationally these transitions are spectroscopy will not be there for homonuclear diatomic. For heteronuclear diatomic, since they have a permanent dipole moment, the transitions are allowed. Okay. So, now since we have discussed the selection rule, let us go ahead and look at the energy and the intensity of the transitions. So, we saw that nu bar j, the wave number corresponding to j level, is given as b j into j plus 1. The selection rule says delta j equals plus minus 1, delta m j is 0 plus minus 1. Of course, delta m j is not going to be playing a role unless we have, these are magnetic quantum numbers, unless we have external magnetic field. So, therefore, the molecule will always be having 2 j plus 1 fold degeneracy. We will not be able to resolve this m j level unless we have external field. So, if this is the nu j bar and the transition is allowed from j to j plus 1. So, therefore, let us find out what is the energy of nu j plus 1, that will be b the j plus 1 into j plus 2, because now the quantum number is j plus 1. So, I am just putting it in the general formula. And what about the delta nu? The delta nu comes out to be the difference between the two. If you do this, you would find this will be 2 b into j plus 1, this quantity minus this quantity. So, now let us see if my j is 0, what about nu bar j? So, if j is 0, the energy of that particular state becomes 0. If j is 1, the energy becomes 1 into j plus 1 2. So, therefore, 2 b. If j is 2, the energy becomes 2 into 3 6 b. If j is 3, the energy becomes 3 into 4 12 b, and so on and so forth. What about delta nu? In this case, the delta nu is given as 2 b j plus 1 or the difference between two consecutive lines. So, in this case, the difference between 2 b and 0 is 2 b. Of course, when I am starting from j equals 0, only I can go to j equals 1. So, that is why now when I am going from 1 to 2, so the energy difference between 2 b and 6 b is 4 b, and the next line the energy difference will be 6 b. So, we see that the transition j equals 0 to 1 will occur at 2 b, j equal to 1 to 2 will occur at 4 b, j equals 2 to 3 will occur at 6 b. If I have to plot a spectrum, so suppose I start from 0, I go 2 b, 4 b, 6 b, 8 b, and so on. So, first transition will occur at 2 b, second one occurs at 4 b, 6 b, 8 b. So, what I see is that they are all equispaced lines. Okay. Now, this is about the energy. What about the intensity? Now, I am just drawing the intensity of all these transitions as equal, but now let us discuss about the intensity of these lines. So, just before that I would just erase this, because so that we have little space to do the discussion. Now, to look up to discuss the intensity, we have to see the intensity would depend on, of course, all delta j plus minus 1 transitions are allowed, j from 0 to 1 or j 1 to 2 all are allowed, but which of these transitions will have more intensity? The answer to that question would come from the fact that at which level, at which rotational level more number of molecules are there. So, what is the population of individual rotational levels? So, we would now evaluate the population of a jth level, jth rotational level with respect to the lowest energy rotational level. So, this population ratio we can use by using Boltzmann's distribution, and this is given as the population of jth level will be proportional to Gj, which is the degree of degeneracy of jth level multiplied by e to the power the energy of that particular state Ej divided by kT. K is Boltzmann's constant at a temperature T, the prevailing temperature is T. Similarly, N0, the population of the ground state, is proportional to G0 e to the power minus E0 divided by kT. What is E0? E0 is the energy of 0th rotational level, but we know when J is 0, the energy is 0. So, this is how we have defined. So, therefore, this term becomes 1, and the degeneracy of the 0th level, the degeneracy is given as 2j plus 1 when j is 0. So, of course, degeneracy is 1. So, therefore, these two terms together they are 1, and therefore, I can write this, the degeneracy of jth level is given as 2j plus 1 e to the power minus E j divided by kT. Now, this is the relative population of Nj. If a particular rotational level will have maximum population, then we would see more transition occurring from that that level to j plus 1 level. So, that particular intensity will become greater. Now, let us look at this function. We see that there is first part of the function 2j plus 1, which increases as j increases. For larger value of j, 2j plus 1 will increase. But we look at the second term, which says e to the power minus E j. So, once the j value increases, the energy value also increases, and the second term, which is e to the power minus of that energy, so that decreases. So, now what would happen is that the population would have would depend on two opposing forces. One is the degeneracy, another is the energy. The greater the energy, less is the population, but greater the energy, greater is the degeneracy. So, therefore, there are two competing forces, and to find out where the maximum will occur, we can take the first derivative of Nj with respect to j and make that 0. When we do that, you will see the root of this equation would come out as will be the j max, the j level where the maximum population occurs. This comes out to be kT divided by 2 hCb minus half. K is Boltzmann's constant, T is temperature, Planck's constant, h and c speed of light, and B is the rotational constant, which is molecule specific, right. So, therefore, J max depends on other universal constants. Apart from that, it also depends on a particular molecular constant, so B. So, therefore, J max is going to be different from a molecule to a molecule. So, depending on what is the value of B, that particular molecule will show a different J max, or the jth level, which will have more intensity. We will just look at this information that is given in this picture. This is for C carbon monoxide molecule. You see it goes from j equals 0 to j equals 14 as I increase 0, 1, 2 up to 14. The next column shows 2j plus 1, this column shows 2j plus 1. The third column shows e to the power minus Ej divided by kT, and the fourth column shows Nj divided by N0, the relative population, and then the final column shows the wave number where it transition happens. So, let us look at, you can see the 2j plus 1 increases as I increase j, the e to the power minus Ej divided by kT, that this term decreases, it starts from 1 and it goes down further. Now, when I multiply the second column with the third column, I see the relative population. You can see the relative population starts from 1. So, therefore, if I say Nj j, so it is j equals 0, it starts from 1, and you see that it increases to 0.98, sorry, it increases from 1 to 2, 7 point something, 8, 8.75, 8.85, and then it starts decreasing. So, I see that 7th level has the maximum population, and further the population decreases. So, this value becomes j max. In this case, I have 7th j equals 7 having maximum population. So, therefore, j 7 to 8 will have the maximum population. So, depending on the population, normally the rotational spectrum appear like this, because at one particular value the J will be J max, otherwise on both sides it would gradually decrease. So, a typical rotational spectrum looks like this, and this is the population versus the J plot. All right. We would now look at some more information about the carbon monoxide molecule. See, here you see J prime to J double prime is the initial state, J prime is the final state. So, 0 to 1 transition occurs in 115 gigahertz frequency. So, gigahertz is also another unit that we normally express our rotational lines. We can alternatively see this nu bar in centimeter inverse. So, let us look at this column. So, 0 to 1 occurs at 115, 1 to 2 occurs at 230, 2 to 3 at 345. You see that this pattern is the difference between two lines is remaining more or less equal, because we know that this difference is equal to 2b, and which is a constant in rotational spectrum. But now when we look the numbers closely, that means that difference between two consecutive lines is plotted here. When you look at these numbers closely, it is of course the in gigahertz unit it is all 115, but look at the points after decimal, you see this is 0.27, 0.26, 0.25, 0.24, 22, 0.20. So, slowly as I am going higher and higher J value, the spacing between two consecutive rotational lines, they are decreasing. Now, why this is a common feature? Why does that happen? So, what I observed is that when I have J for large value of J, the B value decreases. What do I mean by B value? B value is the spacing between two. And why B value is important? Because in rotational spectroscopy, you know that B is given as h divided by 8 pi square c, and then multiplied by the moment of inertia, and in this case I am writing moment of inertia as m r square. M is the effective mass, r is the bond distance in case of a diatomic molecule. So, I see B is inversely proportional to r square. So, if the spacing between two consecutive rotational transitions decreases, that means B decreases, but that also indicates r increases. What is r? R is the distance between the bond distance. Now, I see for large value of J, B is decreasing. So, therefore, R is increasing, and that means my bond distance is increasing. Why would that happen? It is easy to understand, because I have a diatomic molecule. For large value of J, it is rotating faster and faster. Now, when it rotates faster, you can imagine that the molecule is still two atoms held together with some forces. So, the molecule will start going away from each other. You can very well imagine that if you have a stick and you attach two balls on either side of the stick, and you start rotating the stick very fast, you would see if depending on how strongly you attach the two balls in the both ends of the stick, when you rotate it very fast, the two balls will fly away from each other. In other words, the two nuclei are going away from each other. That indicates there is the bond distance is increasing. So, this process, this observation is described in terms of centrifugal distortion. That means, when the molecule rotates faster, there arises a centrifugal force that takes the two nuclei away from each other, that leads to an increase in the bond distance, which is reflected by smaller spacing between two consecutive rotational transitions, and therefore, the B or 2B decreases. Now, how do we express this? To consider this centrifugal distortion, we add one more correction to our nu J term. So, we had J into J plus 1. This energy expression is true only when the molecule is a rigid rotor. That means, the bond distance is very rigid, bond is very strong, it will never stretch. But most bonds are elastic. So, I am sorry, the most bonds are going to show the centrifugal distortion. So, therefore, to add this correction we introduce a distortion coefficient given by d, and this is the expression through which we provide this correction, where d is the centrifugal distortion constant, which is also given as 4 b cube. B is the rotational constant within rigid rotor approximation, and omega is the vibrational frequency of that particular bond within harmonic approximation. So, you can see omega, which is the vibrational frequency, which goes let us say in the order of a few hundred to few thousand wave numbers. On the other hand, B is often a few wave numbers, 1 to 5 centimeter inverse. So, therefore, this value of D is going to be very small. So, this centrifugal distortion contribution is very small, but the effect of this D can be written now. This is the delta nu, the spacing between two consecutive lines. You can see that as j increases, you have this j plus 1 to the power cube to the power 3 term, which is decreasing the spacing between the two. When d goes to 0, we get back our original relation, which was true for the rigid rotor approximation. So, we would just summarize what we did in this class today. Now, we started looking at the rotational spectroscopy of diatomic molecule. We discussed that we said that the rotational spectroscopy of diatomic molecule can be the stationary states corresponding to this can be obtained from a rigid rotor Hamiltonian. So, therefore, the wave functions were the spherical harmonics, the energy values we already had obtained from our quantum chemical discussion. And now, then we discussed the selection rule. We saw that delta j equals plus minus 1 is the selection rule for this rotational transition. We also discussed that although all values of j from 1 to j, all transition that satisfies delta j equals plus or minus 1 can be can show rotational transition, but the intensity will depend on the population of the particular level, and this intensity became a complex function of one increasing contribution, which increases with because the degeneracy increases with increasing value of j. The other factor is the energy increases. So, therefore, there is an exponential minus energy term which reduces the population. So, we found that there is a particular definition of j max, which says that which rotational level will have maximum population. Based on j max, the j max to j max plus 1 transition will show highest intensity. We also saw that rigid rotor approximation is a good enough approximation, but often in cases if we want a very precise molecular structure information, we see that rigid rotor becomes a weaker approximation, and we also provided the correction that can be obtained from centrifugal distortion by this d parameter. So, to describe rotational spectroscopy, we normally use help of b parameter, the rotational constant, and d parameter, the centrifugal distortion coefficient. So, this is the discussion for the diatomic molecules. What happens when I go to polyatomic systems? That will be the topic of discussion in our next class. Thank you for your attention.